So again, I have to thank the organizers, I guess, for bringing me here. And these are now the results from these experiments, what we started quite a while ago. So therefore, the list is long as well. But I mean, for the final experiment, actually, there are rather fewer collaborators now. It's just, so it's Daniel Burchardt, Robert Garthoff, and Kai Redeker. They are still working on it. Norbert Ortegel, he finished his PhD now. And Markus Rau, actually, he is now working for Q-Tools, and he contributed the random number generator. And Benjamin is leading the whole group. So what I want to show you is about the atom-atom entanglement, why we want to use it and how we are using it for this test. But then possibly also you might be interested in some further steps towards the device-independent approach. Although I have to warn you, we are not there yet, by far not, but that's for the end then. Okay, so the starting point was more or less the Bell experiment in Innsbruck, where Gregor Weiss and Thomas Jennewein set up everything to really have independent observers for the first time. And I guess the list on Marissa's slide was too polite, but never mind. And then, of course, also the experiments in the NIST group of Dave Wineland, where the row showed that you can close the detection loophole if you detect the fluorescence of ions, of entangled ions, because there you have an almost arbitrary detection efficiency, and so therefore this can give you this point. And so therefore we tried to combine it and used atoms. Now, neutral atoms, rubidium was for us the choice, because simply it was enough of technology available at this time. Not all, but enough, let's put it that way. And you get entanglement almost any time you excite such quantum states if from some excited state they have two decay channels to some ground states which you then can make indistinguishable in all other degrees of freedom. And with this simply you can get the entanglement here between the internal degree of freedom from the atom, this kind of spin state, whether it's in this -1 magnetic sublevel or in the +1, and the polarization of the photon. And the only trick is to really always correlate the photon, what you collect from your atom or from the NV center from before. So always this type of many channels what you have available can provide you entanglement. You really just have to use it then. Okay, so if you have one atom entangled with a photon, then you just get another setup to have entanglement between another atom and another photon. And now if you combine those two on a beam splitter, then this beam splitting, the interference that the beam splitter selects just one of the Bell states. So actually this Bell state measurement is a projection onto Bell state. So if you have two entangled pairs always, and if you project the index fingers onto a Bell state, onto an entangled state, then the atoms get entangled. So more or less it's about this. But the nice thing is that you don't have if you overlap the photons, there is no limit to the distance anymore. Ideally, of course, and then if you can bridge really long distances. In our case, it will be 400 meters, and we saw it's even longer distances are possible in the Delft experiment. And you can even improve a little because actually this projection onto this interference at the beam splitter just gives you one of the four Bell states. If you do some polarization analysis behind, you also can analyze another Bell state. So effectively this measurement there, this measurement of the photons creates two different entangled states for the atoms, depending on the result what you get there. Okay, and as Ronald already mentioned, it's heralded, this Bell test then, because we know exactly when there is something going on and when we can use the two atoms for the Bell test. So and the original proposal was here already 93, but yeah, it takes a while until the experiments catch up. So very schematic way to draw the experiment now is that we catch such an atom, a single atom, with some means, I come back to this, and another one, and then overlap at the fiber beam splitter. The fiber beam splitter already gives you nice interference quality, at least for the spatial degree of freedom, and then you can make the polarization analysis. And some years ago already we achieved this over 20 meters, and there we also only made this fluorescence analysis on the photons, which is rather slow because it takes a while to collect all the photons, what you need to distinguish whether the atom is in the trap or not, and so on, and therefore, of course, this cannot be called independent observers. But it was already with perfect detection then in those days. So the experiment looks roughly like this, that you have here some glass cell where you have in a magneto-optical trap, which is made up of these red laser beams here. You collect first a cloud of atoms, and then you shine in a strongly focused trap beam, which is far detuned. So it does not induce any transitions between these atomic levels, but just makes a attractive potential at the position where the light is the highest. It's called also atomic laser tweezers or something like this. For biologists, they're using it quite frequently to manipulate their samples. And we are just collecting out of this atomic cloud one single atom. So always if an atom goes through this attractive potential, because it's just a conservative potential, it would not trap on its own, but as long as the magneto-optical cloud is on, this is enough of friction for the atom. Then if it emits a photon while it is in this potential, then it cannot get out anymore. And the nice thing with this is also that actually if there would be another atom coming in, then the two of them, they kick out each other. So they form a kind of light-bounded molecule, which is not stable in this trap. And so this is really a good thing of this experiment, is that you really are sure that in this trap there's always one atom. Either there is no atom or there is a single atom in. And then you need a bunch of other laser beams for the manipulation of state manipulation and preparation and so on. So I guess if we will then once really make this key distribution, Vadim will have his fun with all these many technical details what are involved in this business then. Okay, but we need still these random numbers and some faster detection scheme. And the random numbers now, what we are using is a telegraph signal. What you get if you just have a light source and a single detector. So if every absorption of a photon just switches the state of the signal, and it can be implemented relatively easy, and so there is no magic behind it. I guess that's one of the much simpler task. And it has a very nice feature actually, because these detectors have a dead time, which is usually not what you really want from detectors, but here it actually causes the fact that now we get the random numbers what we use from this telegraph signal, what we sample from it, without bias. So if you do this in the ideal case, for a Poissonian distribution, that's just a property of those, you would always have a higher probability for the even numbers than for the odd numbers. So therefore, actually, this would have a bias. But if due to this dead time, the Poissonian distribution gets more symmetric, and therefore there are cases where then we have a same detection probability or sample probability for even or odd number, and therefore this really can be tuned to no bias, which is actually quite nice, because then we don't need any post-processing. It does not take any additional time until the random number really pops out and so on. Okay, so that was for the random number. For the really fast detection of atoms, we have chosen this rather destructive scheme that we ionize the atom. So we don't really detect the state of the atom, but if the atom is in a particular state, then it gets ionized. And if it's in the orthogonal state, then it just doesn't see the light. So it works like this, that if you have the atom in a certain state, and if you shine in some polarization, then this atom will be excited to this other level, from where then with this blue laser it gets ionized. But if it's in the other state, then it simply does not react to this polarization because it cannot be excited. There is no other level. And so therefore it just is in this dark state. So it's always that the bright state of this atom gets ionized, the dark state simply sits there. And so now you see also that if we shine in another polarization, then we talk to this +1 state. And if we shine in a superposition of these two polarizations, then we simply can analyze also all the other states. So with this, just by tuning the polarization of the light, we can choose which state we want to analyze. We do not have to make any manipulations on the atom itself, but we just make all this via the really defining with the polarization of the light. So, and then it looks about like this. So we have to add all this hardware also into this vacuum cell, which makes another part of headache, but never mind. So in the middle there is about where the position of the atom is, and these are these electron multipliers, which then, where the ion or the electron is accelerated to, and then which causes another avalanche of electrons in these channels there, and then which then finally make you a nice electronic pulse, then, what you can then use. And it takes about 100 nanoseconds to ionize the atom. So if you shine light, this particular polarization and the ionization laser on, that's this red line and the blue line here, then it takes about 100 nanoseconds to ionize the atoms, and this with a relatively high probability. But there you see already that it's not 100% fidelity. The problem is that you also get some off-resonant excitation. So also the dark state, if you shine in light for too long a time, then this will be excited as well sooner or later. So this is one of the problems actually in this scheme. Sorry. And then you get actually the electron detected right away, but the ion, so that's the histogram of detection times for the electrons, and then about this 370 nanoseconds later, then the ion gets detected simply because of the higher mass. It takes a longer time to be accelerated, but around this time there is a very, very narrow coincidence window. So it's really just always around this time where you really this time difference where you detect the two photons, and with a very high efficiency. So if we use choose to detect either the ion or the electron, then we get a detection efficiency of about this number, above 98 or something like this for sure. So now how does the experiment run? So we entangle two atoms with their photons, and because the times what are essential there is roughly this, that we have about 30 nanoseconds lifetime of the atomic state. So which means that we, in order to really get a good time overlap for this interference at the beam splitter, for this Bell state measurement, we also have to synchronize the two experiments on a time scale roughly better than nanoseconds. And then the two photons arrive at the Bell state analysis, which is at the location of one of the two traps, and we get the trigger from. So at this time then we send the message to the other position, and then the measurement starts at some later time. So it's the measurement itself is taken much, much later than the Bell state measurement. But then at the same time again on both sides, first with choosing some random numbers, which which we attribute just some number of 3 samples, because we never saw any correlation from the for more than pair correlation for the next neighbor correlations. So we say that the random numbers are really independent from each other if you just attribute an age of about 70 nanoseconds to them. Then we have to choose the polarization basis, which takes a while because we cannot use the AOMs, which would be faster, but we have to use the EOMs, which would be faster, this Pockels cell, but AOMs with acousto-optic modulator, which can be switched on for a longer time reliably, but it takes a little more time to switch them off on first place. And then we perform the ionization altogether. Sorry for this. Altogether, the measurement time for sure is less than 1 microsecond. And 1 microsecond gives you a distance of at least 300 meters. And fortunately, we found this. So our lab is in this building, and more or less everything what you see here is university area, and almost all the buildings here belong to the university. The problem is they are occupied, of course, and I guess it's at least as bad as at NIST to find free office space there. But fortunately, there was cable channels going along to another place here, and there was a free lab basement, which we then could get the labs into. Good. And then I cannot say that we are celebrating birthday as well in the moment, unfortunately, for our data at least, but because at this time, one of our trap lasers was was broken, and the company to replace it told us it takes a little more than 5 months. They didn't tell us, of course, right away, but at the end it was a little more than 5 months to replace it, but never mind. That wouldn't have been the only problem in our experiment. And so then finally on this 27th of November, then we got this data. What you see here is more or less the cumulative S value. So if we calculate the S value, in this case again we can use the standard Gauss-Horn-Shimoni-Holt inequality. And if you just collect data and data and data, and then you get some S value. And this is this value. And then unfortunately, and the x-axis are actually hours, we have a rate of about 2 per minute roughly. If everything works well, we have about 2 events per minute. But then something happened, some device started to drift, and then even the data for the psi plus, the psi minus was pretty low anyway. Also the psi plus data just got unstable and fell below the value of 2, down to the value of 2. And so actually, if you just use these first few events, then you get very nice values. And so at least this was good to continue with it. But of course, this was, we haven't been happy. And if you are fourth anyway already, so then it's like with Olympics, then you have any time to celebrate your fourth place. Our goal was really to make for all these hypothesis tests that you decide first how the test should run. And for no obvious reason, we decided not to go for 300 events, but for 10,000 events. From these old measurements, we knew that we can run an experiment for quite a long time. And so therefore, we just wanted to go there and did not accept this first data there happily. And so, but after a while then, but only then half a year later, almost, then we got these values. And so again, these are these cumulative S parameters. And here you also see something like the error bars at this time. So the error bars, of course, go down and down and down because you sample more and more, have more and more data. And then after these 5,000 events, finally you get at this value. Now, actually, my people proved to me that if we take always the first 500 events, because I always said, okay, come on, your setup is much better than what it turns out to be at the end. Actually, it turns out if we make analysis of the data from all our runs, and we have many runs where we started and then it drifted away, and always just use these first 500 events and the last 500 events, then they are typically the same. Okay, so even if some results look nice at the beginning, then it's just statistics. I guess this is also what we have to keep in mind, or to me it's quite a nice example why this finite key issue is really important. That for a short number of data, one has to be really careful with. Okay, so this is about 5 days. And with some about 2 hours interruption, but scheduled interruption every day just to get the lasers back on resonance and so on and so on. So these are then this correlation data, and it gives you an S value of about 2.2, and you now know already the importance of this P value, which if we take all the 10,000 events together, then this gives you this about 10 to the minus 10 or 10 to the minus 11, depending on whether you use the NIST or the Delft way to interpret the data, but it's about the same. Okay, so what we also did is, of course, because the data are coming in on such a nice, handy rate, actually we then started one experiment in June where we announced it more or less, that there is now this experiment that if you then connect it to this web page, then you could see the data live coming in. So for the future, you can, we hope that we can soon supply new data. And if you want to look up the old data, then you can download them from there. So everybody is invited to this, what one called p-hacking, whatever. I guess if you want to get news about the next runs, but don't be afraid if it's only in 2 months or so, but then it's there. Okay, so atom entanglement is almost as good as the NV entanglement. It's a little more complicated to me, but perhaps, I mean, it would be as complicated for me as also to make Ron's experiment. Now, for anything going beyond this, there's, of course, some technical challenges like magnetic fields. The subway is some 50 meters away from one of the traps, or actually it just goes in between the two experiments. But this can be handled at least to some level. There are also issues with the dipole trap, but what we also have to be aware for all real physical systems, which don't fully really appreciate all the nice ideas of the theory, is that we really have to take care that we cannot really get all the visibility out what we could get. So again, this is the ideal case where we have from this level we collect the photons if they are emitted in a decay towards this -1 +1 level. We do not collect the photons if they are emitted with this linear polarization, because then they are emitted into a different direction, and so that's not collected. And therefore, we also have very, very high G2 value. So the probability to detect a second photon, if you detect one photon, is really low, but if the atom sits there and it takes a while to excite it fully, then of course you also have the probability that it has already emitted one photon, then can be excited another time. Even if this value is small, it is there. And then there is one nice way, so if it's excited to another level, then so it has this decay first, and then it's excited to this non-resonantly, so it's pretty suppressed, but still there is the option. Then there are decay channels going back to the same state, so actually there you get entangled photons from this atom, which is nice physics, but unfortunately really not really useful. And even worse are those instances where you just emit another pair of those photons, either because you have some non-perfect polarization, or you excite the atom simply because the first emission was not detected anyway when it falls back to the initial state. So because then, and this is unfortunately the highest contribution, because then in this case the time dependence of this interference does not agree anymore between the two photons, and so the temporal mode overlap is just ruined completely, which actually for a particular analysis of our experiment, what we did, would limit this visibility to 92%. And there we really have to be careful, because altogether then we are below this 80%. So actually this is the point where we are just working on it. We hope that improving some of the excitation light and so on, and this level and so on, this business, we get a little above this 80% to get into the realm where we could think of getting some key. On the way towards the quantum repeater, I guess that's really still much further to go. There we really have to then to reconfigure all our trap setups so that we can trap several atoms. It's not so easy like in the NV center business, but then we really have the several atoms there, and then can operate on those more easily. And you see my group there decided to go for it. Thank you.
So I wasn't clear on the 80% number that you just put up, but you had more than 80% already, or no, you're currently at 80%?
No, currently we have roughly 80%, yes. So this is the number, but it just comes out from the product of this imperfect state analysis, because there is this probability to ionize the atom, and also the probability to detect the ions then, or the electron. So all this goes into kind of product, and then of course also then these problems with these higher order contributions.
Is it possible to just pump it faster to reduce the higher order?
Yes, pumping faster is one of the things. We are just simulating and then trying it. Actually, if you pump faster, then you have more off-resonant excitations. Because, yeah, actually pumping on with lower intensity helps more, because this also suppresses the third case better.
Other questions? Yes.
I have a question regarding the random number generator. So you said that you don't have any bias, but how can you make sure that the electronics does not include correlations, like from a low-pass filter of any electronics, that you don't have correlation between the individual numbers?
What do you say, low-pass filter?
I mean, any electronics, any amplifier or so has some frequency dependency of its amplification.
Yeah, but I mean, this the design of this random number generator is in the gigahertz regime.
Excuse me?
It's in the, I mean, all the electronics operates in the gigahertz regime. So there are no low-pass filter. Effectively, you just sample then always again from this telegraph signal, and therefore we are not doing this here. I guess the low-pass filter I wouldn't say. I mean, of course there are correlations actually, because if you have some detection event, then it depends on the time how it fills your sampling intervals. Okay, so we are sampling periodically, and then depending on when there was one detection time, then of course the dead time extends into the other window. So there is a little correlation there, yes. So and that's more or less the reason why we say we're using this 3 sampling, the 70 nanoseconds then. We did not see any correlation beyond this, beyond 50 nanoseconds.
Thank you.
One last question, if we have it. Thomas.
So what was the lifetime of the atom entanglement once you had the atom-atom entanglement? And the related question would be, how far apart could you separate the atoms and still get a violation, say?
I mean, actually we started the measurement 15 microseconds after the first excitation. So you can say at least this time the coherence is pretty high. I mean, if we measure just the coherence of the atoms, then we are, I shouldn't mix up now, I mean, we are almost down at about, at least 100 microseconds, more than 100 microseconds, I would say so. I mean, we never make such long measurements in the moment, because we just want to see when does it fall below 3% or something like this, 5%, just what we can resolve with the measurement. So we don't look for this 1/e position, actually. So, but it's more than 100 microseconds, I would say so. But there are other issues, we can talk about this later, that the dipole trap can make some harms to all the coherence as well. But this is another story. So we only can make the experiments at some time, specific time intervals. So, yeah.
Okay, thanks very much, Harald, and all the speakers.